Okay, so 3.5.3 is going to introduce this complement to position momentum uncertainty, uh, where in the same way that delta x and delta p multiplied is always going to be greater than or equal to h bar over 2, we have a complementary equation here where delta t times delta e is always greater than or equal to h bar over 2. And immediately, assuming that you've taken the canonical order of upper division physics classes, then you should recognize that this is very similar to sort of the 4 vector in special relativity, right? And that's a trap. This is not the same thing as sort of the translation relation between xp and te that you find in special relativity. So let's elaborate on that a little bit. In special relativity, you learned about the 4 vector, and what you found was that there was a 4 vector where the first 3 terms were x positions, right, at position, so x, y, and z, and then the final term was ct. And what you learned was that this could be directly related to another 4 vector in terms of momentum and energy divided by c. So in this way, sort of in special relativity, the relation between x and p requires a further relation between t and e, right? And what that means is that you can shove position and time for a system into this nice little equation and very easily get an analogous representation in terms of momentum and energy instead. So sort of that, if you know about that and you see this relation between these two equations, it sort of makes you think, oh, maybe there's some sort of very easy equation that I can plug uncertainty in x and p into, and out comes uncertainty in t and uncertainty in energy. That is wrong. So the reason why it's wrong is because this comes about as a result of special relativity, right? And so far in quantum mechanics, everything we've learned up to this point, at no point have we ever assumed something to be relativistic. We have strictly been in the territory of non-relativistic systems. If you wanted to introduce special relativity to quantum mechanics, you would get quantum dynamics, which is a significantly more complicated graduate level sort of field. And we will not be seeing that at any time soon. So sort of because of that, we're going to assume that so far everything we've done is strictly non-relativistic. Things are moving very slow. So because of that, this relation, it doesn't even apply. There's no such thing as a 4 vector in non-relativistic physics, right? So this relation isn't even mathematically valid. The second reason why, sort of, if this is a little bit uncomfortable to you, because technically, a 4 vector does exist in non-relativistic theory, it doesn't sort of, you can't really use it because of the fact that there's terms that just go to 0. If that doesn't sit right with you and you want a different explanation, a more mathematically hard explanation would be that from a mathematical standpoint, this doesn't translate into a 4 vector, because if you want to work with the relation between x and p and t and e in a 4 vector, one of the key things that you need is that sort of x and t have to be on the same order. And in our Schrodinger equation, which is our fundamental equation of state in quantum mechanics, you have sort of this first order derivative in time and a second order derivative in position. And the 4 vector does not allow that, right? If x was of a second order derivative and time was of a first order derivative, it literally, they don't plug into the equation that allows it to translate properly into another momentum energy 4 vector. It just won't work. It's mathematically not allowed. So because of that's another sort of reason why this relation is absolutely different and not the same compared to sort of the very easy direct relation between xp and te that you find in special relativity. So automatically, let's just cross that out. Instead, it turns out that sort of this is an entirely different thing. There's no relation between it and xp. It just happens that out of coincidence, sort of the product of the uncertainties of time and energy happen to be greater than or equal to h bar over 2 in the same way that x and p happen to be greater than or equal to h bar over 2. It's sort of a happy little mathematical coincidence, if you will. That being said, it is still worth it to study this, because the delta t here is a very interesting quantity, because sort of traditionally we expect time to be sort of this independent variable, not a dependent one, right? X, P, and E, these three terms, these are all dependent variables that we measure with respect to time. What is the position of a particle with respect to time? What is the momentum of a particle with respect to time? What's the energy of the system at some time t, right? It makes less sense for us to say like, oh, what is the time of a particle? We don't go out and measure the time of a system, right? Like, it's like, oh, what's the time of this ball that's falling down at this speed on this hill? It typically isn't something that we do. So this is automatically interesting to look at just because of the fact that delta t is such an unusual quantity that we use in sort of this direct way of multiplying it or like doing operations with it in direct relation to other quantities. Number two, the other reason why we want to look at this is, what does delta t even mean? Because if you're used to thinking of this as, you think of traditionally of t as the time of a system. So if you see a delta t, sort of the first logical leap is, okay, maybe delta t is the time it takes for me to like measure something, right? Because that's really the only thing that sort of makes sense in terms of like the difference in time. Because the difference in time implies sort of an initial time and a final time. Well, what am I doing at some point, at some time for a system? Well, traditionally I'm measuring something. So the difference in time at one measurement versus the difference in time of another measurement, maybe delta t is the difference in time it takes for me to measure something. And it turns out that's actually false. We're not given a reason for why it's false, but sure, Griffiths is just going to sort of give us this definition, and he's going to tell us, okay, where is my mouse? Hang on, there we go. Griffiths is going to say that actually delta t is the time it takes for a system to change substantially. He doesn't really, give an explanation for why he defines it this way, but it turns out that it is the correct way to do it, and the proof will work out in a very nice way if we define time in that time as this. We don't make this definition, we consider time as instead the time it takes to take a measurement or something like that, then the proof doesn't really work out, it doesn't work, and you're stuck with sort of nothing. So we're just going to take his word and say, okay, sure, I will take your word for this, Griffiths, and I will believe that delta t is in fact the time it takes for a system to change substantially. So that's our first problem out of the way. The second problem is that this is a pretty vague definition, right? What the hell does it mean for a system to change substantially? So the rest of this chapter is going to sort of prove what exactly this means. And we're going to start by considering what do we measure from a system, right? Traditionally, we want to measure observables, right? Position, momentum, energy, so on and so on. So let's consider some observable Q, right? And in quantum mechanics, I can represent this as an operator. So delta t is the time it takes for a system to change substantially. So I'm looking at how long it takes for Q to change. So let's consider, my first assumption is, what if I take the derivative of time with respect to Q? dq hat by dt. This doesn't help me because this just equals 0, right? Because remember, x hat is equal to just x, p hat is equal to negative I h bar d by dx. And as we saw earlier, sort of any arbitrary operator can be represented as some combination of x and p operators. So in that case, since both x and p don't have a direct time dependence, if I take a time derivative of q, which can be decomposed into something in terms of x and p operators, it's still not going to have a direct time relation. It's just going to equal 0. That doesn't help me. So I'm at a dead end here. The next logical leap is, okay, what if instead of taking a time derivative of q, let's take a time derivative of the expectation value of q instead. And this is something that you can actually work with. So let's expand the expectation value of q in bracket notation, in which case we get d by dt of the inner product of psi with q hat acting on psi like this. Then if I shove the derivative into this bracket, right, and use chain rule, this is going to give me 3 terms. This is going to give me d psi by dt inner product with q hat psi plus psi dq hat by dt psi plus psi q hat partial of psi with respect to time, like this. So this gives me three terms. Okay, so at this point, what I can do is I can take advantage of the Schrodinger equation and do a little bit of substitution. So part of the Schrodinger equation, I know that I h bar times the partial of psi with respect to time is actually equal to h hat operating on psi. So if I make this substitution into up here, what I'm going to get is three new terms. So the left term, this is a complex conjugate. So this is going to give, well, let's write this out first. D psi by dt is equal to 1 over I h bar h hat psi, right? So if this is a complex conjugate, it's just going to turn that I into a negative I. So negative 1 over I h bar at the front, h hat psi, inner product with q hat psi. This term is just going to go to 0 because remember the partial of q with respect to t is just equal to 0 as we found over here because of the fact that q hat has no direct dependence on time. So that term I just ignore. This term goes down to plus 1 over I h bar positive this time, inner product of psi with q hat psi. Q hat h hat psi, like that. So at this point, let's just relate this back to the original expression, d by dt of the expectation value of q hat, right? So recognize that h hat is a Hermitian operator, right? So if h hat is a Hermitian operator, that means that I can move this over very simply, and I can say this is actually equal to negative 1 over I h bar of psi inner product with h hat q hat psi, and I'm adding 1 over I h bar psi inner product with q hat h hat psi. If I rearrange this, this is going to give me a commutator. So let's move this around. I'm going to move, let's see, I'm going to move the I to the top. So this is going to give me I over h bar psi inner product h hat q hat psi. This is subtracted by I over h bar inner product of psi q hat h hat psi. This is equal to d by dt of the expectation value of q hat, in which case this is just a commutator. So this is going to be I over h bar, expectation value of the commutator of h hat and q hat. Okay, at this point, so let's rewrite this equation. I have d by dt of the expectation of q hat is now directly related to I over h bar times the expectation of the commutator between the Hamiltonian and my operator of interest. So at this point, let's sort of rewrite this in terms of the commutator instead. So the commutator of h hat and q hat is going to equal h bar over I times d by dt of the expectation value of q hat. And this we can actually plug into the generalized uncertainty principle. Because remember, right, we found way back in the previous section that sigma of h squared times sigma of q squared from the perspective of our generalized uncertainty principle is going to be greater than or equal to 1 over 2i times the expectation value of the commutator of h hat and q hat. The whole thing squared. So our goal here is to somehow turn h into energy and turn q into time. And then show that the resulting equation here is going to reduce down to h bar over 2 up here. So let's start by just plugging in this relation that we just found here into this. So this is going to give us sigma h squared, sigma q squared is greater than or equal to 1 over 2i, right? Multiplied by h bar over I times d by dt of the expectation value of q hat, this whole thing squared. Now, these two terms make a -1, but because of the fact that everything is being squared, I can just throw away that -1. So sigma h squared, sigma q squared is greater than or equal to h bar over 2 times d by dt of the expectation value of q hat squared. So we're pretty close, right? Because if I then just, take a square root, sigma h, sigma q is going to be greater than or equal to h bar over 2 times the magnitude of d by dt q hat. This is pretty close, right? We just have to somehow get rid of this term, or somehow show that it's going to equal 0. So let's define a few things. First off, Hamiltonian is directly related to energy. So sort of the uncertainty in the Hamiltonian quite literally is just the uncertainty in the energy. So this automatically just goes to delta E. We still have sigma q greater than or equal to h bar over 2 magnitude d by dt expectation value q hat, like that. So let's analyze the expectation value of q hat, or sorry, the time derivative of the expectation value of q hat. Because remember, ultimately, a derivative is just equivalent to a change in something with respect to time, right? This is fundamentally equal to a change in q hat expectation over a change in time. So what ultimately is a change in the expectation value of q hat, right? Because that's a change in the expectation value of something. Let's suppose, and this is going to sort of seem like it comes out of nowhere, honestly, in my opinion, but let's suppose that the system changes by some sort of standard deviation, right? So let's suppose that delta q hat, or delta expectation value of q hat, is going to be sigma of q. So let's suppose that it changes, right? Let's suppose that the derivative of the expectation value changes such that in some time delta t, sigma of q is equal to the change in the expectation value of our observable. And Griffiths is going to next say, okay, by definition, I'm going to say that this delta t, by definition, by his definition, is going to be defined as the time it takes for a system, scroll down a bit, for a system to change noticeably, or significantly, I suppose. So what we're interpreting this as is that sort of, okay, the expectation value of sort of the operator q hat has changed by one standard deviation. And Griffiths is going to say, okay, I'm going to define the time it takes for this change to occur to be the time it takes for a system to change significantly. We haven't proven anything. We haven't proven this. We've just defined it in that way. So in that case, delta t is therefore equal to sigma q divided by the magnitude of d expectation value q over dt, where I've taken this equation, I've rearranged it in terms of delta t. So in that case, right, if I then shove that in, then this means that sigma q is equal to delta t divided by magnitude, or multiplied by magnitude d expectation q hat dt. So if I shove that into here, then that means delta E times delta Q, or sigma Q, is going to be turned into delta T times magnitude D expectation value Q hat over dt. And this is greater than or equal to h bar over 2, magnitude D by dt, expectation Q hat, like that. So in that case, these two terms cancel. We just are left with delta E delta T is greater than or equal to h bar over 2. And this is sort of, once again, I'm going to emphasize that this is kind of a weird proof, because we didn't prove something, more so that we got a result and defined it per Griffiths, that this delta t that appears here is going to be defined as the amount of time it takes for a system to change significantly, where significantly is further defined arbitrarily as when whatever expectation value we're measuring, it's or whatever observable we're dealing with, when its expectation value changes by a standard deviation. So we're sort of defining a lot of things by definition, and by doing those definitions, we get this sort of result. So it's by no means sort of a natural proof that just flows out very easily. Rather, we kind of forced this result. We forced this relation by defining delta t in a very specific way. So sort of as a result of that, this is once more going back and showing that, this proof, this is a very arbitrary expression, where delta t was defined in a very arbitrary way. So whereas the delta x delta p proof sort of flows out very naturally from sort of the generalized uncertainty principle, this thing does not come naturally. We sort of forced our hand to do this by sort of defining delta t in a very specific way, once again further proving that sort of these two expressions do not have the same relation that these two expressions normally would have if we were dealing with a relativistic system, and because of that, sort of emphasizing that this is not a relativistic system. We are strictly working with quantum mechanics in a non-relativistic system, not a relativistic one. So with that, let's move on to the examples. Okay, example 3.5, I'm not too big of a fan of, all things considered, because it sort of tells you to just sort of trust it, that certain things are true and that they'll be proven later down the line in problems. And I don't really like it when it does that, but regardless, let's just go through with it. So this example tells us to consider the logical extreme of a stationary state, where your energy is determinate and expectation values are always constant with respect to time. So what this is telling you is that delta E is equivalent to 0 and delta T is equal to infinity. Delta E is 0 because of the fact that your energy is determinate, so energy is always going to take the same value always, right? So because of that, there's no standard deviation in energy. Energy is just a single value. In response to that, because of the fact that delta E is 0, delta T for some expectation value to change with respect to time is going to be infinity, because of the fact that constants are, or it's because of the fact that this example tells us that the expectation values are always constant in time. So if the expectation values don't change, the time it takes for the system to change substantially is going to be infinite, because it's never going to change. And this example is asking, okay, so in this extreme scenario where delta E equals 0 and delta T equals infinity, does that energy time uncertainty principle of delta E delta T being greater than or equal to h bar over 2, is this still true? Because it seems like here, if delta E equals 0 and delta T equals infinity, we have an undeterminate value, right? So let's try to prove this. So what we're going to do is, because of the fact that we can't just multiply these two directly, we're going to try and construct an arbitrary wave function that meets the requirements of what we were talking about. So the requirements is that this is a stationary state that has determinate energy. So let's build an arbitrary wave function consisting of two wave functions that has energy 1 and energy 2. So determinate values of energy, where energy takes on the values of E1 or E2. I'm going to say, okay, psi of x comma t is going to equal some constant a times psi 1 purely in x times the time component e to the negative I e1 times t divided by h bar. And we're going to add this with b psi 2 purely in x, and then the time component e to the negative I, this time a secondary energy e2 times t divided by h bar. So this is just a wave function that's a combination of two stationary states, representing therefore two possible energy states, right? So for simplicity, we're going to further assume that a, b, psi 1, and psi 2 are all real, so that way if I take the magnitude squared of this term, it sort of simplifies very nicely into just a squared psi 1 squared plus b squared psi 2 squared plus ab psi 1 psi 2, and then sort of the combo of the exponentials. So I'm going to rewrite this as exp of negative I times t divided by h bar E2 minus E1, and then the opposite version of this, which is going to be plus exp of positive it over h bar E2 minus E1. So at this point, one thing that we can do now is we can sort of rewrite this in terms of a cosine, because this is very clearly sort of an exponential representation of a sinusoid, right? So we know that for a complex value z, cosine of z can be represented as the exponential of iz plus the exponential of negative iz, all divided by 2. So in that case, this term, so this means that 2 times cosine of z is equal to the exponential of iz plus the exponential of negative iz. So in this case, z is going to be this inner term, right? So this is therefore going to equal mag psi squared is equal to a squared psi 1 squared plus b squared psi 2 squared plus ab psi 1 psi 2, and then the cosine version of this complex exponential, so cosine of E2 minus E1 divided by h bar, all multiplied by t, like this. So the thing specifically that we're looking for now, or this thing that we're paying attention to specifically, is this cosine term, because this is going to come out to just be a constant. This is going to come out to just be a constant, right? And sort of the thing that ultimately matters is the fact that this wave function is going to oscillate with respect to time according to this cosine term. So because of that, right, our information in regards to delta E and delta T, sort of, you know, the uncertainty or the sort of the standard deviation with respect to the system is mainly going to come from how the wave function itself behaves. And since this wave function is ultimately dictated by this cosine term, our goal is to study this cosine term a little bit more. So this is a cosine term. Its period is going to be tau is equal to 2 pi divided by the constant. So this is going to be 2 pi times h bar divided by E2 minus E1, right? And this is the part I don't like, because Griffiths is going to say, okay, take my word for it. It turns out that the standard deviation in energy for this system is going to be delta E is actually equal to E2 minus E1. And it also turns out that the time it takes for the system to change substantially is going to equal 1 period, or tau, which is equal to 2 pi h bar E2 minus E1. So this I can believe, right? The time it takes for this system to change substantially is going to be based on this cosine term, because this is the only term that sort of varies with respect to time. So therefore, one entire period represents one substantial change in the system. It's sort of, if you try to logic it out, it seems very arbitrary, which is why, once again, I don't like this example very much. But it's sort of understandable. But this sort of idea that the standard deviation in energy is the difference between E2 and E1, this is something that you're not going to be able to understand why this is a thing until you actually do the problem 3.20. So until you actually get to it, Griffiths is basically going to say, just take my word for it. You know, delta E, or the standard deviation in energy for the system, is going to turn out to just equal E2 minus E1, and the time it takes for the system to change substantially is going to turn out to just be the period. But yeah, we're just taking his word for it. Either way, later down the line in 3.20, we'll actually prove it mathematically and see why this is the case. But until then, this implies that delta E multiplied by delta T is going to equal E2 minus E1 multiplied by 2 pi h bar divided by E2 minus E1, in which case this is just equal to 2 pi h bar, which is indeed greater than or equal to h bar half. Therefore, this condition, which the logical extreme of the stationary state, where there's determinate energy and, you know, the expectation values never change with respect to time, it still follows this rule, because ultimately we derived a system that satisfies this conditions, and when we try to analyze it by taking delta E, delta T, we ended up with this value. So with that, let's move on to the next example. Okay, example 3.6 is going to look at instead a free particle. So it's going to, Griffiths says, suppose that the time it takes for a free particle to pass through a point in space is delta t. So delta t is equal to the time taken for particle to pass a region, let's call it delta x. So in that case, velocity, right, is equal to the change in position with respect to time. So it passes through this region delta x with respect to some delta t. So in that case, I can rearrange this and say that delta t is in fact equal to delta x over v, right? So then, if I then rewrite velocity in terms of momentum, then this is in fact equal to m delta x over p. Remember, p is equal to mass times velocity, right? So I just found delta t, or I just defined a delta t for this system, this free particle system, in which I'm saying, okay, the time it takes for this system to change substantially is the time it takes for this particle to pass through this arbitrary region delta x. Once again, very sort of arbitrary definition for delta t, but that's sort of what we've been doing so far, is doing this very arbitrary definition to force sort of this relation between delta E and delta T to be true, right? So next, let's note that the energy of a free particle is just going to equal to p squared over 2m, right? So in that case, dE by dt, if I take a derivative, by chain rule, this is 2p dp by dt, dt, or sorry, not dt, over 2m, right? So the 2's cancel, this is equal to p dp by dt over m. In which case, if I get rid of the dt and say just the change in energy, then delta E is in fact equal to just p delta p over m, right? So in that case, delta E times delta t is going to equal p delta p divided by m times m delta x over p. The p's cancel, the m's cancel, what we're left with is delta x delta p. This is literally just the uncertainty relation between position and momentum. By definition, this is already greater than or equal to h bar over 2. Therefore, our hypothetical system of a free particle does indeed obey sort of this requirement of delta E, delta T being greater than or equal to h bar over 2. Once again, sort of this expression, once again, I wish to sort of re-emphasize this, but this expression is a very sort of forced expression, as we've seen when we proved this at the start of the section, where sort of the definition of delta t itself is sort of arbitrarily stated to be the time it takes for the system to change substantially, and our definition of substantially is arbitrarily defined in such a way so that delta t equals what it is. So in this case, we arbitrarily define delta t to be the time it takes for this particle to pass through some region delta x. And with that, let's move on to the final example. Okay, example 3.7 is a very nice sort of real-world example of the implications of quantum mechanics. So 3.7 tells us to consider a delta particle. So a delta particle is one of those, I don't remember enough about particle physics and all that stuff to know exactly what it constitutes, but it's one of those sort of theoretical particles on the Standard Model that sort of decays very quickly. Basically, if you make one, it'll pretty much radioactively decay into some more stable particle after some period. That specific period that we're talking about is delta t is equal to 10 to the negative 23rd seconds. So on average, it takes about this long. If there is a delta particle in existence, it'll last about this long before it decays down either into pure energy or some other more stable particle configuration, whatever that may be. So if you measure its mass, right, if we were to have some sort of super advanced machine that could measure the mass of the delta particle as soon as it comes into existence, your measurement of mass, typically, if you had, a bunch of them, like hundreds of thousands or millions, right, it doesn't have a well-defined mass. What you're going to find is that it has this is the resting mass, where you can say mc squared is equal to 1232 mega electron volts per c squared. This is the actual value this is its actual rest mass if you sort of plug it into sort of the E equals mc squared formula for a delta particle. And what you'll find is that the masses that you measure for all these millions of delta particles follows a normal distribution / bell curve centered at the rest mass. And the width of this bell curve is roughly 120 mega electron volts per c squared. And the question that we're asked in this example is, why does this happen, right? Why is it that when you measure the mass of a particle, sometimes it's sort of significantly less than the expected rest mass of the particle, and why is it sometimes significantly more? Because if you think about this, right, the width of this thing corresponds to 1 standard deviation, right? The width of a bell curve is 1 standard deviation. So what that means is that in this width, strictly speaking, assuming that this is a perfectly normal distribution, this corresponds to about 60% of all your observations on a statistical in like a statistical view, right? So that means that you're pretty likely to find one of these particles with a mass that is as different as 10% of its expected rest mass. Because if you look, like 120 divided by 1232, that's almost on the level of 10%. So like imagine, measuring the mass of like of a ball, and you expect it to be like 10 pounds, but every once in a while you measure a ball and it'll be like 9 pounds or like 11 pounds. On a macro scale, that really doesn't seem to make sense, but on this way smaller microscopic scale, the reason why this happens is primarily because of the intrinsic nature of sort of this uncertainty principle. Because think about what delta T tells us, right? In this case, the rest energy, or delta E, the standard deviation energy, is going to be just 1 standard deviation of this bell curve, which is going to be the width divided by 2. So 60 MeV over c squared, multiplied by delta T, the time it takes for the system to change on some significant scale, which in this case is going to be the time it takes for it to decay away, so 10 to the negative 23rd. And the result for this is going to give you roughly something like 6 times 10 to the negative 22nd MeV. And if you actually consider the minimum possible value, because remember this has to be greater than or equal to h bar over 2, well, it turns out h bar over 2, if you actually plug in h bar in terms of mega electron volts, this is going to give you something like 3 times 10 to the negative 22nd mega electron volts. And this value is only twice as big as the minimum value. On standard systems, the product of delta E, delta T is typically significantly larger in magnitude compared to the minimum value of h bar over 2. So what that tells you is that in this system, it's already getting very close to the minimum possible uncertainty that you can get. So it's just a very nice representation of sort of quantum mechanics actually being real, because so far sort of everything we've seen so far has been limited to the realm of mathematics and theoretical problems and whatnot. We haven't really seen real life examples very, very often in terms of things that actually are affected by quantum mechanics, because of the fact that just quantum mechanics is really only prevalent on very small scales, macroscopic levels, compared to macroscopic levels, I should say. So in this case, this is just a very nice real-world example of something that does in fact behave in a quantum mechanical way, which is that, in this case, because of the fact that this thing has such a short lifetime, I suppose, in which it can exist, because of that, it literally, there's not enough time for it to obtain a well-defined mass. So because of that, its mass can sort of fluctuate when you measure it, because of the fact that this sort of bell curve is extremely wide compared to something like a normal particle. Because if you looked at a normal particle with and like measured, if you measured like 1,000 protons or like 1,000,000 protons, the resulting graph you would get would be like, this is the mc squared expected value for a proton, and the actual the histogram that you would get if you measured like 1,000,000 of them would look much more similar to something like a Dirac delta well, something like this, right? Where it's just it's so narrow that you can barely see it. But for something like this, where delta T is so small, the corresponding delta E has to get way larger. So because of that, the uncertainty in energy corresponds to an uncertainty in its mass. So because of that, now all of a sudden this well, or this bell curve gets way wider because of the fact that delta E is just so much bigger now to compensate for the fact that delta T is becoming so much smaller. And I believe with that we are done. So now we will move on to the actual problems.